Hello, everybody. Today's lecture, we're going to learn about a very important topic to geotechnical engineers called the Atterberg limits. And this relates to soil consistency of fine-grained soils. So we're not really going to talk about coarse-grained soils today, like sands and gravels, but we're only going to focus on silts and clays, in particular clays. So Albert Atterberg was a soil scientist back in I believe the 1800s. I could be wrong, but he's from Scandinavia, and he developed a system of measurements to evaluate the water content related to the different phase changes of the soil. So in other words, you remember being a kid and going outside and playing in the dirt. You would fill it up with water, and then you create mud, and you'd want to play, make mud patties and those kinds of things. But so even little kids understand that when you add water to soil, it changes the consistency and the texture of the soil. And so Albert Atterberg wanted to understand the science behind that and to develop a consistent set of standards by which we could define the different phase states or consistency states of soil. The reason engineers care about this stuff is because ultimately at the end of the day, we're concerned about how the soil behaves under different moisture contents. And more importantly, we're concerned about the different engineering properties of the soil. So if there was a way that we could correlate or estimate the engineering of the properties of the soil and relate that back to moisture content, that would be a really useful tool to have. And so we use these boundaries or Atterberg limits to correlate a lot of these different engineering soil properties. So the Atterberg limits basically work like this, where if I plot on the y-axis soil volume and on the x-axis moisture content, what we see is that if I start adding a little bit of moisture to the soil, there's going to be a portion where we don't see really any change in the volume. But if I keep adding moisture, eventually what's going to happen with a fine-grained soil is it's going to start increasing in volume, and it's just going to keep increasing. The more water I add, the more volume the soil has. And so this behavior is what Albert Atterberg observed. And he defined these boundary lines that define the different states or consistencies of the soil. So the first consistency state is that of a solid, and then that of a semi-solid, that of a plastic, and finally that of a liquid. So the boundary that defines the zone between the solid and the semi-solid state is what we call the shrinkage limit, or we call it an SL. And so below this water content, the volume of the soil remains constant. Then the boundary that defines the state between semi-solid and plastic behavior of the soil is called the plastic limit, or PL. And we define the plastic limit today as the water content at which the soil just barely begins to crumble and crack when you roll a little snake at 1/8 inch diameter with the soil. Then the boundary between plastic and liquid behavior is what we call the liquid limit. And this is the moisture content at which a groove cut into a soil patty in a liquid limit device will close over a 1/2 inch width at exactly 25 taps of the liquid limit device. Now you're probably wondering what in the world I'm talking about with liquid limit device, and we'll get to that in a few minutes. And then finally, the plasticity index, it really isn't an Atterberg limit, but it's something that we derive from the Atterberg limits. The plasticity index is simply the liquid limit minus the plastic limit. It's the difference between the two. So first we can talk about the liquid limit. There are two tests used in the world today to measure the liquid limit. The device or the test that I was referring to earlier is the test in the Casagrande liquid limit device. That's this little device down here that I circled. So you can see there's a little cup that we place the soil in and flatten it out and make a little soil patty. We cut a groove in the soil and we turn the crank, and each time we turn the crank, that little cup is going to bop against the base of the device. When we cut the groove into the soil and we start bopping it, the liquid limit is the moisture content that will cause the soil to close the gap at exactly 25 bops of the device. So this is the test, or at least the testing apparatus that is used most commonly in the United States. An alternative device that's used more in Europe and Asia is called the fall cone device. I'm not going to talk too much about that other than it's a nifty test. They drop a cone from a known and a constant distance down into the soil. There's a line drawn on the cone, and the liquid limit is the moisture content in the soil at which the cone drops exactly to the line drawn on the cone. So these are the tests that are used today, but mostly in this class we're only going to talk about the Casagrande liquid limit device. Now this is a YouTube video. I'm not allowed to show this video on my YouTube video for copyright infringements, but I have the link down below in the description box, and I encourage you to go click on that link and watch how this liquid limit test is performed. It's obviously a student in a soils lab at some university, and I think it's a nice demonstration of how the liquid limit test goes. So, some of you may be thinking, wow, that's really hard. How in the world am I going to get the moisture content just right so that at 25 bops on my liquid limit device, the gap is going to close? That seems like it would be really hard to do. And you're right, it is hard to get exactly 25 bops. So there's two methods that we do instead to get the liquid limit. The first method is one of interpolation, and we call it the flow line technique. So with the flow line technique, we're going to do 3 liquid limit tests, but we're going to try to get everything but 25 bops. So what we're going to do is we're going to add basically enough water that we're going to get something far less than 25. So for instance, in this example, we got maybe 18 bops the first test, and then we measure the water content and we get something like 48.8 or something % moisture content. Then the second test, we're going to add a little bit of water, a little bit more, so we get fewer bops, so maybe we get 23. And then the third test, we're going to add more water, and now this time we get 30. All we're doing is taking these 3 lines and we're going to fit a linear line, a best fit line through those 3 points, and then we interpolate the moisture content that corresponds to 25 bops. And that's our liquid limit. So that's how we do it, and we don't need to get exactly 25 bops. The second method that I'll just talk to you about is the one-point empirical correlation. And this method isn't used very often, but it can be handy if you're stranded on a desert island and you need to estimate a liquid limit to somehow get off the island or to save your life or something. So basically all you're going to do is you're going to put in the 1 bop that you got and the water content associated with it, and it's going to spit out an approximation of the liquid limit. This relationship was developed from hundreds and hundreds of actual liquid limit tests on different soil types, but you need to be aware that this is an approximation. It's a statistical relationship. It's empirical. It's not an actual or precise estimate of the liquid limit. So I don't know anybody who uses that equation in actual design. So talking about the plastic limit, to get the plastic limit, we're going to take little balls of the soil and we're going to play with them and roll them until the soil starts to feel like it's getting pretty stiff, to the point where it's not as plastic anymore and might be a semi-solid. At this point, we're going to start rolling little worms of about 1/8 inch diameter. And we know that when we roll, if we get it down to 1/8 inch diameter and the soil starts to just get a little cracky, a little flaky around the edges, then that means we're right at the plastic limit. So chop that little snake up, put it in a can, and maybe cover it with a moist towel to keep the moisture in it. And we want to do it enough until we get maybe 6 grams of soil. That's about what's necessary to measure a plastic limit. So I have some tips down here, tip 1, tip 2, and tip 3. These are just useful tips that will help you when you roll your plastic snakes, because to be honest, this kind of takes a little bit of practice. But somebody who's really good at the plastic limit can roll these snakes out really quickly, and it's remarkable how repeatable and consistent these plastic limits can be. Okay, so now we've completed Atterberg limits. We've measured the plastic limit. We've measured the liquid limit. Now, Arthur Casagrande, the same individual who developed the liquid limit testing device, went and plotted on the x-axis the liquid limit, and on the y-axis the plasticity index. You'll recall the plasticity index is the liquid limit minus the plastic limit, for hundreds and hundreds and hundreds of soils that he had. And what he found is that soils of different types tended to congregate in regions on this chart. And he also noticed a couple of other things. For instance, he noticed that no soils ever plotted above this line, which he called the U line, or the upper limit of all known soils. He also noticed that he could separate different types of soils, basically the clay-like versus the silt-like soils, using this line that he called the A line, or the Atterberg line. And so this line generally separates clay-behaving type soils from silt-behaving type soils, and it also separates inorganic clays from organic clays. So these Casagrande plasticity charts can be very useful, because say you perform a test on a soil that you have, you can plot the Atterberg limits on this chart and get an idea of the behavior of that particular soil. So I have an interesting question for you then. If we can tell that a fine-grained soil is a clay or a silt from just a plasticity chart and the Atterberg limits, why in the world would we ever want to perform a hydrometer test, which is a lengthy test and pretty involved? And the answer to this question really is that the two tests measure different things. The hydrometer test is measuring the composition of the soil, or in other words, it's measuring the actual particle diameter of the soil. Now, the Atterberg limit test doesn't measure the composition or the diameter of the particles at all. Instead, it's measuring the behavior of the soil in the presence of water. So the tests are really complementary. The Atterberg limits are an indicator of the behavior of the soil, but not the composition. The hydrometer test is an indicator of the composition of the soil, but not necessarily its behavior. So why are Atterberg limits useful? Well, for one, Atterberg limits can be a great indicator of soil sensitivity. Soil sensitivity deals with, of course, sensitive soils. What's a sensitive soil, you might ask? Well, if I were to plot, let's make a nice series of axes here. Okay, so on this axis I have, let's say axial strain, and on this axis, let's say I have applied shear stress. So if I plot this type of behavior for any given soil, I might have a soil that looks like this, and we'd call that, strain hardening. I might have a different soil that might look something like this. And then we might call this type of behavior strain softening. And it's more common with stiff, fine-grained soils or dense, coarse-grained soils. But the point is that it reaches some peak at some strain, and then after you pass that strain, the strength of the soil decreases, and it takes less stress to get it to deform. Now, there are certain types of strain softening soils that show some pretty dramatic drops in shear strength. And these types of soils that show dramatic drops in shear strength are what we're going to call sensitive soils. So a sensitive soil, therefore, is a soil that loses more than 8 times its undisturbed or peak shear strength when you strain it. So you can understand why engineers might want to know whether or not a soil is going to be sensitive. So Atterberg limits can help us because we can calculate what's known as the liquidity index. The liquidity index is calculated as the moisture content minus the plastic limit divided by the plasticity index. Now, if the liquidity index is greater than, wrong button. If the liquidity index is greater than 1, then it's a good indicator that the soil is a sensitive soil. And so it can help us understand whether or not we may have a problem and might want to perform some more testing. If the liquidity index is well below 1, then it's a good indicator that the soil is probably stiffer and isn't going to show that sensitive behavior. Another thing that's useful with Atterberg limits is using it to compute what's called the activity of a clay. The activity is an indicator of how active the clay is in the presence of water. And we compute it as the ratio of the plasticity index to the percent clay fraction. And that percent clay fraction is what we get from a hydrometer test. So once we compute the activity, research has shown that different clay minerals like montmorillonite, like illite, or like kaolinite generally fall within ranges of different activity levels. So if I have an activity level that's 1 or greater, that's telling me that that clay is pretty active in the presence of water, and that I might have some problems like with shrink swell, or it might be pretty sensitive to certain ions that might be present in the soil, or that I might be adding to the soil. So it might be an indicator I need to do some engineering on that soil. However, if I compute an activity that's less than 0.5 maybe, or 0.4 or less, that's telling me that the clay mineral in that clay is probably pretty inert and is not going to react extremely with water when water is introduced. Atterberg limits can be a good indicator of whether or not my soil is going to have a problem with swelling or shrinking. So swelling occurs when I add water to clay, and shrinking occurs when I take water away. If the soil has a plasticity index that is greater than 20, then we're probably going to have a soil that is prone to shrink swell. If the PI is less than 20, I still could have a shrink swell problem, but it's more likely if the PI is greater than 20. Also, Atterberg limits can be a good indicator of the stress history of the clay. If the liquidity index is greater than or equal to 1, that probably means that the soil is what we call normally consolidated. This means that that soil has never felt more stress, more vertical stress in its existence than it is feeling right now. So it's the most stressed it's ever been. But if the liquidity index is less than 1, then that's an indicator that the soil has been more stressed than it currently is at some time in its past, which means that the soil could be strong, and may not be as prone to settlements and deformations, and may have a higher shear strength. So finally, Atterberg limits, as we talked about before with the plasticity chart, can be useful to classify and name different soil types. So using a classification system like the Unified Soil Classification System, the Atterberg limits can be used to assign names to different soils. And these names are very useful, allowing us to communicate with each other and to understand a little bit about the properties and behavior of the soil just by its name. And so we're going to talk a little bit more about soil classification in the next lecture, but I just want to introduce the idea right here. So with that, that's the end of the lecture. I want to thank you for your attention and look forward to seeing you in the next lecture. Thanks.